When two opposing processes are occurring at the same time and at the same rate, the system is said to be in equilibrium. In this state, the rate of the reverse process is equal to the rate of the forward process. So if you're looking at the picture of my two guys blowing their driveways here, one is going to the left and the other one is going to the right. And since they're both have the same style of snowblower and blowing the same amount of snow at the same rate, they're really going nowhere. Actually, they're just filling in the pathway of what they're doing there. So we have something going on. The one person's blowing snow in one direction, the other one's blowing it in the other direction, and there's no real net change in the amount of snow on the driveway. It's just staying the same. The same thing is true about equilibrium. We've actually discussed two different equilibrium systems before. The first one on the left here shows a liquid, those green little particles moving all around. We have a liquid that's trapped inside of a container. We fill it up and then we put a stopper on it. And we know that liquids like water and ethanol or alcohol will actually readily evaporate. So they evaporate up into that trapped space above the liquid. And as the vapor pressure builds, when those particles strike the surface of the liquid, they can get reabsorbed or actually turn back into the liquid phase. And so we have evaporation and condensation happening at the same time inside of the container. After a while, the level of liquid will stay constant because the rate at which the substance is evaporating and the rate at which the substance is recondensing is the same. When that water level inside the container stays the same, we would say that that's now in phase equilibrium, that the liquid and the gas they're changing, the liquid's changing to a gas and the gas changing to a liquid at the same rate, but the level of water, the line that would be across there, would actually stay the same. There's another type of equilibrium when we're actually dissolving a salt inside of a liquid like water. And we know that salt particles will actually dissolve, or we call it solvation, where the water molecules will surround the positive and negative ions and kind of carry them away. But if we keep adding more and more and more solute, eventually we're going to get a pile of undissolved solute on the bottom of the solution. And the amount of solid will stay the same. We can stir that solution until our arm falls off, and we're still not going to be able to get that last little bit to dissolve because the solution is said to be saturated. In a saturated solution, we actually have what we call solution equilibrium, because even though we have undissolved material on the bottom, there's still going to be particles that are going to be escaping and being dissolved through the process of solvation. But at the same time, when those particles strike the surface of that crystal there, they could actually get rebonded onto that crystal, and which we call desolvation, or they're basically recrystallizing. And this process would go on over and over and over again. So when you have a saturated solution with a bunch of solutes sitting on the bottom, if you walk away and come back 2 hours later, it's still going to be the same amount of salt that's sitting on the bottom of the container, but it's not going to be the same salt. Some of that salt will have actually dissolved, and some new salt will have recrystallized over time. So those are two examples of an equilibrium process that we already know about. We've talked about in previous chemistry classes. The third one that we've already talked about is gas solubility, and this slide probably looks familiar to you because we actually talked about it during our solutions unit. The most common way to talk about gases dissolved in a liquid would be in soda cans, because it's something that we see every day. You have a gas that's over the surface of a liquid, and they pressurize that gas to get a whole lot of it to dissolve inside of the solution. But even when the container here is sitting on the shelf waiting for you to buy it, you have a lot of dissolved carbon dioxide, but it will actually try to come out of that solution into that airspace, that space that's over the top of the can. Because of that high pressure, though, that gas will then redissolve itself into the liquid here. And so by increasing the pressure of a gas over a liquid, that will cause more of that gas to actually dissolve. But what ends up happening here is that the gas will still be escaping into that space above the can right here, and it'll also be redissolving into the liquid over time. Now, what happens when we open up the can is we actually release that pressure And what happens is the dissolved carbon dioxide can then come out of solution. So you see all these little bubbles right here in the solution. That's the carbon dioxide trying to escape out of the soda and trying to reach a new equilibrium point. However, since the pressure of 1 atmosphere is so much lower than what it had before, essentially almost all the gas ends up escaping out of the liquid because that equilibrium is just destroyed from the opening of that soda can. So the last thing I want to talk about with equilibrium is a chemical reaction that actually can go in reverse. A reversible reaction is a reaction in which the conversion of reactants to products and products to reactants occurs simultaneously. So you have I have a reaction of SO2 and oxygen here. So I have these substances, right? SO2 and oxygen. SO2 and oxygen will readily become SO3 when they're combined together. So we'll actually form into SO3 over here. But the SO3 at the same time likes to turn back into SO2 and oxygen. So these two processes happen simultaneously back and forth. And so anytime that you get if you fill a container with SO2 and oxygen, eventually you're going to see a whole bunch of SO3 being formed inside the container. But since the SO3 also likes to turn back into SO2 and oxygen, you never get the container to totally turn into SO3 when you start out with SO2 and oxygen. What ends up happening is these processes are going back and forth simultaneously, and you reach this equilibrium point where you have a certain amount of SO2, oxygen, and SO3 that's at equilibrium, and that would be the middle picture there where you have all three of those substances together. So if it is left undisturbed, the reaction proceeds until the rate of the forward reaction is equal to the rate of the reverse reaction. If this occurs, the reaction is said to be in a state of chemical equilibrium. When equilibrium is achieved, no net change in the actual amounts of those substances occurs. So when I have that middle picture where I'm at equilibrium, where both of these processes are going back and forth at the same rate, the amount of SO2, O2, and SO3 is going to stay exactly the same, even though there's still SO2 and oxygen becoming SO3, because the SO3 would be turning back into SO2 and oxygen at the same rate. So these things are going back and forth, back and forth, back and forth, but it happens simultaneously and so quickly that it looks like the amounts of those three substances actually doesn't change through the process. Now, note, even though that the forward and reverse reaction rates are the same, the actual equilibrium concentrations of each component do not need to be the same. So just because we're at equilibrium doesn't mean you're going to have equal amounts of those three substances. The relative concentrations of the reactants and products at equilibrium constitute what we call the reaction's equilibrium position. And this equilibrium position could be just a tiny amount of SO3 being formed, or it could be a large amount of SO3 formed in the process. It doesn't matter where you start, though. If you start with, like on my picture here on the left-hand side, my little graph, I start with 50% oxygen, and I start with 100% concentration of SO2, and I combine those two gases together. There's no SO3 in the container whatsoever. The amounts of SO2 and O2 are going to go down. The SO2 is going to fall twice as fast because you need two SO2s with one oxygen to become SO3, and the amount of SO3 is going to go up. However, eventually they'll reach a point where those amounts flatten out. And you'll notice that the amounts are not exactly the same. Their concentrations are not the same. We actually produced a large amount of SO3, but we still got some SO2 and O2 on the bottom. But when those three lines flatten out, we are now at equilibrium. Even if I went backwards, now the second graph here is the best one I could find, but actually it should be flipped around. It shows time going in this direction. So we're starting with 100% SO3 and no SO2 and oxygen. Over time, this SO3 amount will start going down a little bit, and the amounts of SO2 and oxygen will increase. But when they start to flatten out right at that point there, the solution is now at equilibrium again. It reached that same equilibrium position where the relative concentration of SO3 to SO2 and oxygen is the same when I started with just SO2 and oxygen on the left-hand side. So the point I'm trying to make here is that that when the substance reaches equilibrium, or when the reaction reaches equilibrium, the amounts of each of the reactants and products doesn't change, but it doesn't necessarily mean they have to be the same. It just means that they're not changing when we reach that equilibrium point. And that ends our second flip lesson on equilibrium.